In this lesson, which is part 2 of our Lewis dot structures, we're going to continue what we talked about. In part 1, we talked about how to arrange the electron dots and figure out which electrons are going to be paired up and shared. In other words, how to play Cupid to make those single bonds. And then we figured out how to do the Lewis structures and the structural model of those for some simple molecules. Now, there's other parts to that, and one thing we'll have to deal with is we didn't do any with carbon in it yet. Carbon and some of its other similar elements are little special cases, so we're going to talk about how to deal with those guys. And then we've only made single bonds so far, but in this lesson, we're going to do some examples to show you how double and triple bonds work. So carbon is a little bit of a special case in that it undergoes something called hybridization. Now, we'll just touch the tip of the iceberg about this, and in a later lesson, we'll dive into a little bit more details. But to first understand this, first I want you to start by drawing the electron dot for carbon. Okay, so if you're drawing the electron dot for carbon, well, carbon's got 4 valence electrons, so this is the way we would draw it for the carbon. And then I ask you to do the orbital notation for it as well. So there's our orbital notation for carbon. It has the first energy level filled, and here are its 4 valence electrons. 2 of them are paired up in the s, and then we have the 2 individually in the p's, which is why we draw the structure this way to show these 2 paired up. These represents the ones in the 2s, and then we have our 2 unpaired ones, which represent these guys that are in the 2p's. Now, drawn this way, how many bonds would you expect carbon to be able to make? Okay, well, using what we have learned before in part 1, we were always pairing the unpaired electrons, and so we would expect carbon to be able to make 2 bonds if this were the structure when it bonded. However, when we look at actual molecules that contain carbon in them, and there's lots of them, we find that carbon actually makes 4 bonds all the time. And so we have to account for this somehow. So the structure must not be like this when it goes to bond. So to answer this question, our model says that carbon undergoes something called hybridization. Okay, and the word hybrid means to mix. Maybe you have a hybrid vehicle which runs on a mixture of gasoline and electricity. Or maybe you remember about Mendel and his pea plants when you learned about hybridization. They're mixing some different species. So what our model shows the carbon doing is taking these and mixing them together so that we end up with 4 orbitals that are all the same. They're neither s's nor p's. They're actually a mixture of them. And so they're each 1 part s and 3 parts p that we mix together, and so we call them sp3 orbitals. Now, don't get too hung up on this now. There'll be a later video where we dive more into that. But the important part for us to know here is that now all 4 of these orbitals are the same in terms of their energies, so it's able to spread all of these second energy level electrons out as opposed to pairing up and just having the 2 pairs. So this model allows us to think of the electron dot notation of carbon as this way with 4 separate valence electrons. So bottom line, if you don't get too hung up on all the hybridization stuff, is from now on, whenever you're drawing the electron dot for carbon, you want to draw it this hybridized way where it has all 4 of them spread out. And so now we can see carbon now has the ability to make 4 bonds, which we know it does from looking at all the compounds that exist in. Okay, now you might guess carbon is not the only element to do this. As we know, elements in the same column tend to behave the same way. So carbon's in group 4, so we might expect silicon to do the same thing, and it does. Okay, these are the 2 main ones that you're going to see, because as we move down this column, we tend to get things that are more involved. They become more metallic, and so they tend to be more in ionic compounds and not in covalent compounds. So it's mainly these 2 guys that you see. And it's not only group 4 that we see exceptions in. If we were looking at group 3, if we looked at an example of boron, so if I was drawing boron, okay, I would do it this way. It has 3 valence electrons, and my electron dot for boron would look like this. There's my 3 electrons in the second energy level. But again, in looking at compounds that contain boron, we see that boron typically has 3 bonds, and this model doesn't allow for it to make 3 bonds. So again, boron will hybridize its orbitals. Now this time, since it only has 3 electrons, it only needs to mix 1s with 2 p's to have 3 orbitals to spread those 3 electrons out. So it's got 1s and 2 p's, so we call those resulting orbitals sp2 orbitals because they're now 1 part s and only 2 parts p because we only needed 3 of them total. Again, don't let that bother you too much. Bottom line is, from now on, when you're doing the electron dot for boron, draw it this way to show all 3 of our electrons spread out, and so it can share these to make 3 bonds. So let's take a look at an example that actually combines a couple different things that we're going to be looking at this lesson. And let's look at H2CO, and I'll work through this with us here. So I look at the structure here. I've got 3 elements, hydrogen, carbon, and oxygen. Of course, I want to put the middle guy in the middle, and if you got carbon, he's always in the middle. So we'll go ahead and I'll do my scratch work again. I always want to do my scratch work to figure out how this goes. So I'll put my C in the middle, and then I'm just going to surround it with everybody else. So I've got 2 H's and an O. We're just going to surround it with that. Again, doing my electron dot. So carbon, we're going to draw now the new hybridized way. So there's my electron dot for carbon. Hydrogen each has 1 valence electron, and oxygen has 6. And no matter how I rotate it, I should always have 2 pairs and 2 unpaired for oxygen. Now I'm ready to play Cupid. Again, I'm not allowed to connect those 2. So let's just pick and start pairing here. So maybe we pick this one, and I'm going to pair that one with the unpaired one there on the carbon. And let's pair those guys up. And then I have this one here. Again, I can't pair these 2, but we can go ahead and pair that one with the one on oxygen. And then I have 2 more that are unpaired. So let's go ahead and pair those guys up. And at this point, we now have everybody paired up. Now it looks a little funky, so let's clean it up and draw the Lewis dot and see what that looks like now. So again, I always start with my guy in the middle. I'm going to draw my carbon in the middle. And up on top here, carbon is sharing this pair with the hydrogen. So I'm going to draw that pair, and then we'll just tractor beam that hydrogen up, clean it up, put that right on top of the carbon like that. And then the carbon is sharing another pair over on this side with this hydrogen. So I'll just tractor beam that hydrogen in. And there's my H with that pair that's shared. And then this carbon and the oxygen are sharing some electrons. So I'm going to draw this O here. Now in this case, they're sharing this pair, but the same carbon and the same oxygen is also sharing this pair. So there's a grand total of 2 pairs that are shared between this carbon and this oxygen. So I'm going to draw 2 pairs between the carbon and the oxygen. And this, of course, is what we call a double bond, because single bond is where you just have 1 share paired between 2 atoms. So here we have 2 single bonds, but in this case we have 2 pairs that are shared. So that's called a double bond. And then, of course, we want to make sure we always include all of our electrons. So I'm going to draw those in as well. Now this looks a little funky, but remember our 2 check questions from part 1 to see if this is correct. Number 1 is, does everybody have an octet? And remember, hydrogen is good with just 2. That's its version of an octet, so hydrogen's good. If I look at this carbon, does it have access to 8 electrons? 1, 2, 3, 4. All 4 of these are going back and forth, so it has access to these 4. So yes, this carbon does have an octet, as well as this oxygen has access to an octet. So yes, everybody has an octet. And then we want to do an electron count. Okay, we had hydrogen that each brought in 1, so 2 electrons total from the hydrogen. Carbon has 4 valence electrons, and the oxygen had 6 valence electrons. So we have a grand total of 12 electrons to play with. So let's make sure that we only have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got the right number of electrons. Everybody has an octet. We're good. Now drawing the structural model for this. Again, we've got our carbon in the middle. I have my single bond to the two H's. And then since we have two pairs that are shared, we're going to draw our two dashes. Remember, each dash represents two electrons. It represents a shared pair of electrons. So this here represents those 4 electrons that are in between the carbon and the oxygen. And then I want to make sure I'm always drawing all of my electrons. So there's my final answer for my structural model with the double bond and my hybridized carbon. So now we want you to go ahead and do that example. Okay, so let's see how you did on this one. I gave you the structure of this because it's a little bit strange, but our carbons are always in the middle. And so drawing the electron dot, we have our hybridized carbon with the electron dot spread out. Nitrogen has 5 valence electrons, so it has 3 pairs. Again, I used my trick of always rotating the unpaired electrons towards the middle. So I put my pairs on the outside. You don't have to do that. It just makes it way easier to figure this out. And then we have to play Cupid. And there's a lot of unpaired electrons here. So when we go to play Cupid, the only way that ends up working is to pair them up this way. Okay, if you don't do it that way, then you'll end up with some 2 unpaired ones on the same nitrogen. And remember, you cannot pair 2 on the same nitrogen. So we get something like this. So again, looks a little funky here, but when we clean it up, you can see I have a triple bond between this carbon and this nitrogen. There are 3 pairs that are shared. So when I draw my Lewis dot, there's my 3 pairs that are shared between that carbon and that nitrogen. Now there's only 1 pair that is shared between our 2 carbons. So there's my pair that's shared between the 2 carbons. And then finally, we also have 3 pairs between this carbon and this nitrogen. Don't forget to draw your other electrons on the end. If we do our octet check, does everybody have an octet? It looks weird, but yes, this nitrogen has access to these 6 plus these 2. This carbon has access to these 6 plus this 2, and the same on the other side. So everybody has access to their 8 electrons. This looks pretty cool when you draw the structural model of it. There's my triple bond. There's my single bond between the 2 carbons, and I have the same thing on the other side. If we do an electron count, we should have a grand total. Each nitrogen brings in 5, which is 10, plus 4 from each. We should have a grand total of 18 electrons on our structure. And if we count them, 2, 4, 6, 8, 10, 12, 14, 16, 18, which tells us our structure is good. Okay, one last case that we have to look at is the situation with some of the group 3 elements and the octet rule. Let's say we were doing the structure for BF3. Okay, so we have boron, and that's one of our other guys that hybridizes. It only has 3 valence electrons, so it spreads those 3 electrons out into those sp2 orbitals. Okay, again, bottom line is we have to draw it this way. And then we have 3 fluorines. So I surrounded it with my 3 fluorines. Again, I rotated it. My lone electron is towards the middle. And so now we have to play Cupid. And playing Cupid means we're going to pair these guys up. So when I clean that up, I have my boron sharing a pair with each of these 3 fluorines. And so now I just went straight for the structural model to save us some time here. So here's the pair that's shared with each of the 3 fluorines. Don't forget to draw all of your electrons around the fluorines. So we're good here. And I'm all out of electrons at this point. Now again, before I move on, I'm always asking myself my 2 check questions. Does everybody have an octet? Okay, and this fluorine looks great. There's its 6 plus 2 gives it 8. All my fluorines are good. But when we look at the boron, we see that it only has access to 6 electrons. And when we look back at our scratch work, there's really nothing else we can do. There's no other way we can connect these. There is no way that boron is going to get an octet in this structure, in this molecule. And, anytime we have rules, we have exceptions. So we have the octet rule, or your group 3 elements are sometimes exceptions to that octet rule. So when you draw your structure and you're asking, does everybody have an octet? If you've got one of your group 3 elements and it will almost always be boron. Might rarely be aluminum, but mostly aluminum is ionic. So boron and aluminum are about the only guys that are okay if they only have 6. So there you go, your exceptions to the octet rule. Of course, we've already talked about hydrogen and why hydrogen only gets 2 electrons around it because it's in the first energy level. So for your final practice, go ahead and draw. We have our diatomic elements down below. So hydrogen is H2. So go ahead and draw the structural and Lewis dot model. What would H2 look like? What would O2, Cl2, and N2 look like? Hope that helps. It gets easier and easier with practice. Eventually, you'll think this is pretty easy.